Hello everyone, and welcome back to the series on single variable calculus. Today we're going to be continuing our exploration of different integration techniques that can be used to find the antiderivatives or definite integrals of some functions that are integrable. So I just want to give you a brief heads up. Make sure you do understand your basic techniques of integration, in particular u-substitution, integration by parts, partial fraction decomposition, and most of all the fundamental theorem of calculus. So in the realm of trigonometric substitutions, it pretty much follows the same exact vibe as u-substitutions, but with the trick, I guess you could say, of using trigonometric functions when trigonometric functions are not necessarily present in your derivative. So there are a couple identities that you definitely need to know in order to be proficient at trigonometric substitutions. The first is the classical sine squared theta plus cosine squared theta is equal to 1. And also 1 plus tangent squared theta is equal to secant squared of theta. There's also a third one, 1 plus the cotangent squared of theta is equal to cosecant squared of theta, but technically speaking, the first two are the most important. A couple others that are commonly used also, but can also be bypassed by mixing these three with partial fraction decompositions, are your hyperbolic trigonometric identities, which are given by hyperbolic cosine squared of theta minus hyperbolic sine squared of theta is equal to 1. And the last one that I want to mention is 1 hyperbolic tangent squared of theta is equal to hyperbolic secant squared of theta. And obviously there is a sixth one that you should be able to maybe guess if you are familiar with hyperbolics, but these first two are going to do just fine. So the example that I want to illustrate first with trigonometric substitutions is the following integral, which actually is pretty easy to solve. It's the integral of 3x times the square root of 5 plus x squared dx. Now, you actually don't need to use trigonometric substitutions for this. For example, you can solve this with u-substitution. Let u be equal to 5x squared. Its derivative is a linear function. The linear function is in front of that radical, so you should be able to use u-substitution on this. So if you want to sort of work that out so you can sort of see what the answer we're going to be aiming for is in the end, I definitely recommend pausing this video and sort of trying that out on your own. So instead of using u-substitution, I want to sort of show you how trigonometric substitution can be used for this same type of integral so that at least you can trust that it gives you the right result if you compare it to the answer that you get with u-substitution. So the very first thing that you definitely need to understand when hopefully using trigonometric substitution is identifying when you can use it. So if you look underneath this radical function, obviously the square root of a quadratic is a little bit annoying to deal with. So definitely looking at that function portion is definitely a good thing to look at. You might also look at this and say, okay, well if that 5 was actually 1, this is pretty much similar to 1 plus tangent squared of theta. So maybe if we let x be equal to tangent of theta or something in order to target that 5, maybe that would be a good substitution, right? And indeed that will actually work, but if you don't know it will work, then obviously you need to explore, try it out on your own, and convince yourself that it will. So what we're going to do is we're going to let x be equal to the square root of 5 times the tangent of theta, right? So just the tangent of theta. So why are we letting x be this? Well, obviously x is equal to some function of theta because it's something plus x squared. So, 1 plus tangent squared is equal to secant squared of theta. The square root of secant squared would just be secant. And then we can, solve that hopefully in an easier manner. And the square root of 5 is actually going to allow us to target that little 5 term because when we square the square root of 5, we just get 5, and maybe we can factor that 5 out and make things a little bit more nicer. So let's actually work through this math and sort of see what happens. So if x is equal to the square root of 5 times the tangent of theta, then dx would just be equal to the square root of 5 times the secant square root of theta d theta. So then we know what dx is, and we can just replace that in this particular expression. And we know what x is. So if x is equal to the square root of 5 tangent theta, that means x squared would just be equal to 5 times the tangent squared of theta. So what does this integral turn into? So this is going to be equal to what? So let's just leave that x there just temporarily. So we're just going to be left with 3x. And then what are we going to have? So we're going to have the square root of 5 plus x squared. So 5 times the tangent square root of theta, and then dx, that's going to be equal to the square root of 5 times secant squared of theta d theta. So let's see if we can clean this up just a tad bit. So firstly, that 3 and that square root of 5 are just constants, so I just want to pull that out temporarily as well, just to simplify this a bit. So that's going to give us 3 times the square root of 5 as a coefficient, times the integral. Let's bring it back our x. Hopefully that cancels out in the near future. So that's going to be equal to the square root of 5 times the tangent of theta for that term x there. And then what I want to do is factor out a 5 out of this term. So that's going to be the square root of 5 times 1 plus tangent square root of theta. And then we still have that secant square root of theta at the end times d theta. So let us see what we have here. So we have square root of 5, and then we have another square root of 5 there. That's going to be equal to 5, and that's going to give us a total of 15 square roots of 5 as our leading coefficient. And then we're going to have the integral of the tangent of theta, and then we have the integral of 1 plus tangent squared, that's secant squared, so the square root of secant squared will just be secant. So we're going to have secant of theta, and then we have that secant squared of theta, and then we're going to have d theta there. And then you're like, okay, well, what can I do with this? So if you notice that we have 3 secants in total and 1 tangent, if you don't really know what to do when you have a bunch of trigonometric functions like this, a nice place to sort of guess or play around with is first off write everything in terms of sine and cosine. So I'm going to do just that to sort of see what happens. So that's going to be equal to the integral of sine of theta divided by cosine of theta. Secant is just 1 over cosine of theta, and then secant squared, that's just going to be equal to 1 over cosine squared of theta, and then d theta. And now notice that we have 4 cosines on the bottom and 1 sine on top. So let's just write that and see if we can do anything with it. So we have 15 square roots of 5 times the integral of sine theta all over cosine of theta. I'm going to write that to the power of 4. And then d theta. And this is pretty much the only thing you can do at the present time. So now you're like, okay, well, what can I do with this? Well, we know that the derivative of sine is cosine, and the derivative of cosine is negative sine. And if that's cosine, its derivative is practically on the top. So maybe I can use a u-substitution here to proceed onwards. So we started off with x, then we converted to theta. Now we're going to go from theta and turn it into u. So let's see what happens with that. So let's let u be equal to the cosine of theta. So du will be equal to minus sine of theta d theta. So that means d theta will be equal to du divided by minus 1 times sine theta. So there's our d theta differential for which we can replace. And then we can hopefully cancel something out. So this is going to be what? So that's going to be 15 times the square root of 5 times the integral. So we still have our sine theta on top. And then on the bottom we have u to the power of 4. And then d theta is now du divided by minus 1 times the sine of theta. So notice that these sine theta terms do cancel, so we don't have to write sine theta in terms of u, which is actually pretty nice. And of course, don't forget that little minus 1 there, and let's throw it in the front so we do not forget it. And then we're just going to be left with an integral in terms of u only, right? So that means our integral of interest is going to be negative 15 square roots of 5 times the integral of u to the minus 4 du. So that's actually pretty nice. Now we can just use the power rule in terms of u, and that's going to give us what? So we're going to have minus 15 times the square root of 5 times, so add 1 to that, that's going to be minus 3. So we're going to have u to the minus 3 divided by that new exponent. And then we're going to, have our plus c as usual. Now we can simplify this because 3 definitely goes into 15 evenly. And we also have a double negative that's going to turn into a positive as well. So what we have here is our integral is going to be 5 square roots of 5 times u to the power of minus 3 plus c. And now we need to reverse engineer all of our substitutions. So keep in mind that u was equal to the cosine of theta. So that means this is going to be equal to 5 times the square root of 5 times the cosine of theta to the power of minus 3 plus c. So that's one way to represent it. Right, so this is in terms of u. This is in terms of theta, and now we just have to reverse engineer one more substitution. So remember that x was equal to the square root of 5 tangent of theta, which means that theta will be equal to the arc tangent of x divided by the square root of 5. So substitute that in, and then we're going to have our integral will be equal to 5 square root of 5 times the cosine of the arctangent. Let's throw this in brackets. So the cosine of the arctangent of x divided by the square root of 5 to the power of minus 3. And keep in mind that minus 3 is applied to the cosine, not the interior, plus c. Technically speaking, this is your answer. But it's definitely not the nicest of answers. Not nice. And if you took my recommendation and solved the original integral with u-substitution, then you probably did not get this answer. So the next question is, well, is it possible that we can write this in a nicer way? And the answer is yes. And the trick to do that actually comes from the integral that came immediately before it, the one that has the cosine of theta inside of that representation. So let's think about what's going on with this cosine of theta representation, just for a quick moment. So if we draw a right triangle here, let's call this, for example, theta. What are we going to have here? So keep in mind, tangent of theta from this x substitution is going to be equal to what? So that's going to be equal to opposite over adjacent. So x divided by the square root of 5. So opposite of this triangle would be x, adjacent would be the square root of 5. So what would that hypotenuse be? So that would obviously come from the Pythagorean theorem, so I'm going to call that hypotenuse r. So r squared is equal to a squared plus b squared. So that's going to be 5 plus x squared. So that means what? So that means r is going to be equal to the square root of x squared plus 5. Right, so that's going to be our r value. And what do we actually want? Well, we want the cosine of theta. So what actually is the cosine of theta? Well, the cosine of theta is going to be equal to adjacent over hypotenuse, and adjacent equals the square root of x squared plus 5 all over the hypotenuse. No, that's not the adjacent. The adjacent is the square root of 5, and the hypotenuse is this newfound thing, the square root of x squared plus 5. And we can substitute that into the expression for cosine, and hopefully get something a little bit more nicer. So let's actually take a look and see what that actually comes out to. So if we look at our integral representation in terms of cosine, keep in mind, let's just rewrite it just in case you forgot. So it's 5 times the square root of 5 times the cosine of theta to the power of minus 3 plus c. So this is going to turn into what? So we have 5 times the square root of 5, and then the cosine of theta. Well, what's the cosine of theta? It's this little radical little looking thing. So that's going to be equal to the square root of 5 divided by the square root of x squared plus 5, all raised to the power of minus 3 plus c. Now, although there's a lot of square roots in this, it's definitely a lot nicer than that other thing that we had before. So what I'm going to do now is I'm just going to reciprocate this since we have a negative exponent, so when we flip it, it becomes positive. So that's going to give us 5 square roots of 5. On the bottom, we're going to have 3 square roots of 5, so I'm just going to write square root of 5, square root of 5, square root of 5. And on the top, we're just going to have x squared plus 5 to the power of 3 divided by 2, plus c. So what do we have here? So we have square root of 5, that's canceling. Square root of 5 times the square root of 5 is 5, and 5 divided by 5 obviously is 1, so that cancels. And then we're just left with this actually very friendly looking integral. So if we sort of go back to our original problem, which was the integral of 3x times the square root of 5 plus x squared dx, through trigonometric substitution, and also u-substitution if you did it that way, just gives you x squared plus 5 to the power of 3 halves plus c, which is actually a very friendly looking integral. But of course you could have found this with u-substitution, but now you can sort of see the math and potential complexity and intensity that trigonometric substitution comes with integration. But this example, obviously you could have done in an alternative way. Let's do another example where u-substitution probably might not be as trivial as this example. So now let us consider the integral of dx divided by the square root of the quadratic x squared minus 6x plus 13. So obviously it's not really in the form 1 plus something squared, and it's not really in the form something squared plus something else squared either, in order to trivially use any trigonometric substitutions. Also, since there's no linear function on the top of this rational or multiplied on the bottom, a u-substitution also doesn't appear to be exactly trivial as well. So every time that you have sort of a quadratic just sort of chilling, minding its own business, usually a good approach to do is using a technique that you probably learned in algebra or pre-calculus known as completing the square. Right? In case you know any math fundamentals, this completing the square technique was used to build the quadratic formula and also was used to write the equation of a parabola in its standard form to represent its vertex a little bit more clearly. So before we get into any serious calculus, let's complete the square on this and see if we can turn it into something that's a little bit more manageable. So we have that x squared minus 6x plus 13 is our expression. So the trick for completing the square is you take the number in front of x, so our magic number in front of x is going to be minus 6, take that divided by 2 and then square it. So a number in front of x divided by 2 and square it. So that's going to be minus 6 divided by 2, that's going to be minus 3. Minus 3 squared is going to be 9. So that's going to be our magic number. So what do we do with our magic number? So what we're going to do is we're going to take it, we're going to add it and subtract it to our expression. Because when you add 0 to anything, it doesn't really change. Now what's magical about this relationship is if you group the first 3 together, this always factors extremely nicely. Because if you look at this, this is just the same as x minus 3, the quantity squared, and then minus 9 plus 13, that's just going to give us positive 4. Right, so this is the alternative representation of the denominator of our expression. Another thing that I want to do is factor out a 4 out of this expression. Now you might be thinking, how can I factor out a 4? Well, I can write this as x minus 3 to the power of 2 divided by 4 plus 1. And we also know that 4 is the same as 2 squared, so I can actually represent this as 4 times x minus 3 divided by 2, the quantity squared, plus 1. So this thing that was underneath the square root, x squared minus 6x plus 3, has now been represented as 4 times something squared plus 1. So what does this something squared plus 1 reminisce of? Well, it kind of looks like tangent squared theta plus 1, which then gives us, oh, I can use a trigonometric substitution on this, and hopefully it turns out well. Right? So let's use this newfound knowledge and see if this helps us turn our integral into something a little bit more nicer. So let's rewrite our integral. So we have the integral of dx divided by the square root of x squared minus 6x plus 13. And we've found that this is equivalent to writing this as dx divided by the square root of 4 times x minus 3 divided by 2, the quantity squared plus 1 underneath that radical. Now keep in mind the square root of 4 is going to be equal to 2, so I can factor that out as a 1/2 in front. And then what I want to do is I want to let's do tangent of theta is going to be equal to that inside x minus 3 divided by 2. So then that's going to give us 1/2 as our coefficient, and then the integral of dx over the square root of 1 plus tangent of square root of theta. Right? We already know that the square root of 1 plus tangent squared theta is just equal to secant of theta. So we can write this as 1/2 times the integral of dx divided by secant of theta. But keep in mind we cannot just do the integral of dx over secant theta because that's just the integral of cosine of theta, but it's with respect to x, not theta. So we need to represent this in terms of a differential of theta so we can continue this integration process. So let's differentiate both sides of this equation with respect to x, or implicitly differentiate this. So the derivative of a tangent of theta is going to be equal to the secant squared of theta d theta, and over here the derivative of x minus 3 divided by 2 is just going to be equal to 1/2 dx. So we can solve this equation for dx actually quite easily. So dx will be equal to 2 times the secant squared of theta d theta. So now we have our differential of x represented in terms of theta only, so then we can substitute this over and then continue our integration as usual. So we're going to have 1/2 times the integral of 2 times the secant squared of theta d theta divided by 1 secant of theta on the bottom. We clearly see that one of these secants cancel, and that 2 and that 1/2 also eliminate as well. So this integral that we have has actually turned into something extremely nice. It's equal to just the integral of secant of theta d theta. Now, most people should already know the closed form representation of the integral of secant of theta. You should know that that's just equal to the natural log of the absolute value of secant theta plus tangent theta. You should know that formula from just basic antiderivatives or derivatives of chain rule types of functions. But if you're not familiar with this rule, try taking the derivative of this expression. You will get secant of theta. But I think that's a very important rule that you just should know, just as much as you know the derivative of sine to be equal to cosine. So now that we have this expression, notice that this integral is in terms of theta, not x, and we definitely want this to be in terms of x, not theta. And remember that the tangent of theta, which was our substitution, was equal to x minus 3 over 2. So we could multiply both sides by 2. Actually, we could take the inverse tangent of both sides of this expression, substitute that into both of these thetas, and we're going to get a super nasty looking thing. But you can do the same right triangle trick like we did before to get a nicer representation. Because all we need to do is just figure out, okay, well, what is secant of theta? What is tangent of theta? Where theta is equal to this particular expression here. So tangent of theta equals opposite over hypotenuse. So the top of this expression will be our opposite over adjacent. So that's going to be opposite over adjacent, right? So that's going to be our opposite. So that's going to be x minus 3, and our adjacent will be 2. And then what will be the hypotenuse? Well, the hypotenuse will, again, from Pythagorean theorem, be the square root of the sum of those two things, which is going to be equal to x minus 3 squared plus 2 squared, which is going to be 4. But you should recognize x minus 3 squared plus 4, so r actually is going to be equal to just the original square root expression that we had before, x squared minus 6x plus 13. Isn't that pretty neat? Right? So if that's the case, well, what is the secant of theta? So secant of theta, keep in mind, is 1 divided by cosine, and cosine is equal to adjacent over hypotenuse, so this is going to be hypotenuse over adjacent. And tangent of theta, again, is opposite over hypotenuse, which we already have. That's just x minus 3 over 2. So what is hypotenuse over adjacent? So hypotenuse over adjacent is just going to be equal to the square root of x squared minus 6x plus 13, and the adjacent is just going to be equal to 2. So that means we can go and replace secant of theta and tangent of theta with x minus 3 over 2 and this little fraction right here. We can just substitute those directly into this expression, and then we have our integral in, I guess you could say, one of the nicer forms. So therefore, the integral of dx divided by the square root of x squared minus 6x plus 13 will be represented as the natural log of the square root of x squared minus 6x plus 13 all over 2, and then plus x minus 3 all over 2, and don't forget your lonely little integration constant plus c at the end. And that would be your beautiful result. The last thing that I want to talk about today is actually a special case of a trigonometric substitution known as the Weierstrass substitution. And the Weierstrass substitution is u is equal to the tangent of x over 2. And you might be thinking, well, that's a strange choice of a substitution, isn't it? And you might be right. Some people call this one of the more clever substitutions that one can perform. Now, before I actually go through an example of when you can use this and why it is so quote-unquote clever, I just want to sort of build some of the theoretical things of why the substitution actually works. So if we take this substitution as our choice, for whatever reason, you should be able to solve this equation for x. In particular, x will be equal to 2 times the arctangent of u. So if I differentiate both sides of this equation, I'm going to get dx is equal to 2 divided by 1 plus u squared du. right? So if I use this u substitution, I'm always going to get a differential of x represented in terms of a function of u only. Now you might be thinking, well, isn't that pretty much the case for pretty much all substitutions? For the most part, yes. But there's a really important point that I want to make here, and it'll all come together at the end, right? So that's the first thing that you should note. So if I choose u to be tangent x over 2, dx will always be equal to 2 divided by 1 plus u squared du. So keep this formula in the back of your mind. This is going to come in handy later. Also, if 1 plus u squared is equal to, if we use this value of u in this expression, that's just going to be equal to 1 plus the tangent squared of x over 2, which is the same thing as the secant squared of x over 2 as well. Right? So keep this identity in the back of your mind as well. And also, there's another identity that we need to use just briefly, and that's the double angle identity for sine. And you might remember that sine 2 theta is the same as 2 sine theta times the cosine of theta. And if we replace theta with x over 2, then what we're going to have here is the sine of 2 times x over 2, well, that's just going to be equal to x, right, is going to be equal to 2 times the sine of x over 2 times the cosine of x over 2. And remember that sine of x over 2 is the same as cosecant of x over 2's reciprocal. So we can write that as 1 over, actually I want to write the 2 on the first one. So 2 and then cosecant of x over 2. And then what is cosine? Well, cosine is just going to be equal to secant. So secant is going to be 1 over secant of x over 2. And then what are we going to have? Well, secant of x over 2 is just going to be equal to the square root of 1 plus u squared from this identity. So the secant of x over 2 will just be equal to the square root of 1 plus u squared. Right? So we can actually just replace that in this particular expression. And using some other identities that you should already know, you should be able to find an equivalent representation of the cosecant of x over 2 also in terms of u only. Right? So if I replace that, that's going to be equal to 1 over the square root of u squared plus 1 for the first term. And for this term, you're also going to see that that's going to be 2u all over the square root of 1 plus u squared. So I leave to you as an exercise to prove that the cosecant of x over 2 will be equal to u divided by the square root of 1 plus u squared. Right? So that's a little fun little exercise to sort of work on your trig identities. Okay? So when we have this, what we have here is that sine is equal to the product of these two fractions. So if we simplify this, notice that the bottoms are both the square root of u squared plus 1. So when we multiply the square root of something times the square root of something, you just get something in the end. So therefore, what do we have? So therefore, the sine of x is going to be equal to 2u divided by 1 plus u squared. Right? So that's the second important thing that I want to mention. And similarly, there's another identity for cosine that you can prove on your own. And the cosine is going to be equal to 1 minus u squared all over 1 plus u squared. So this is going to be the third important piece of this puzzle. And keep in mind, these pieces of these puzzles only work under the Weierstrass substitution, or potentially others, but definitely the Weierstrass substitution. And let's just remember the first piece of this puzzle, and it was dx is equal to 2 divided by 1 plus u squared. All right, so piece 1, piece 2, and piece 3. Okay, so let's bring this together and see what kind of integrals we can solve with this so-called wonderful Weierstrass substitution. So if we have an integral of the form, let's call this arbitrary function f, that only has sine and cosine in it. So we have a bunch of sines and we have a bunch of cosines, and we don't really know how to solve that with an integral. Then, if we let u be equal to the tangent of x over 2, we have another way of representing sine, we have another way of representing cosine, and we have another way of representing dx in terms of u and u only without x. So that means this will be equivalent under this substitution of f of, so sine of x turns into 2u all over 1 plus u squared, cosine x turns into 1 minus u squared, 1 minus u squared all over 1 plus u squared, and dx turns into 2 over 1 plus u squared du, right? And this is done via this Weierstrass substitution, right? So that means what? So that means integral with sine x and cosine x turns into an integral that is a rational function in some new variable u only, right? Because that's a rational function, any composition of them will also be a rational function. Here we have another rational function and hence rational, right? So if you know how to do partial fraction decomposition, then it might be likely that Weierstrass substitution will turn it into something that you can solve with that. So now that we know the important pieces of our puzzle, now let's do an example using the Weierstrass substitution. So here we have this very friendly looking integral, the integral of sine x over 1 plus sine x. And we're also wanting to find a definite integral from 0 to 2 pi. So how would you do this? I don't know. So one observation, obviously, is you only see variables in terms of sine and or cosine. Yes, there's no cosine in here, but if you did see a cosine on the bottom, like cosine plus sine, then that also is okay. So if you only see sine and or cosine, then the Weierstrass substitution is always a good move to use because it's always going to turn it into a rational function, and we've already proven that. So what we're going to do is we're going to let u be equal to the tangent of x over 2. Okay? So when we let u be equal to x over 2, then what do we have? So we already know that sine of x is going to turn into 2u divided by 1 plus u squared, and dx will always turn into 2 divided by 1 plus u squared times du. Yes, cosine x turns into something else, but we don't have any cosines in our expression, so I'm only going to mention sine and dx here. Right? So now what I want to do is I want to look at my bounds and transform them as well. But keep in mind, u is equal to the tangent of x divided by 2, and tangent does have some vertical asymptotes. In particular, pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So you clearly can see that x cannot be equal to pi, 3 pi, minus 3 pi, and so on. And generally speaking, x cannot be equal to 2k plus 1 pi, where k is an integer. And if that's the case, keep in mind we're going from 0 to 2 pi, and pi is in the middle, and pi is a bad point. So we cannot use the fundamental theorem of calculus on this integral. We have to split it up into two integrals and introduce improper integration, right? So this is obviously an improper integration or improper integral because for our substitution we do have a vertical asymptote on the interior of our domain. Okay, so we're going to build some bounds. So we're going to go from 0 to pi from the left, and then we're going to go from pi to the right to 2 pi, right? So we're going to have 4 numbers of interest to evaluate in our limits, right? For our particular substitution of u is equal to the tangent of x over 2. And you might want to pause this video and try this on your own because this is a very important improper integral thing. So we're going to look at x is equal to 0. X is equal to pi from the left, so that's in terms of limits. X is equal to pi from the right, and then we're going to look at x is equal to 2 pi. All right, so when x is equal to 0, what are we going to have? So that means u is going to be equal to the tangent of 0 divided by 2, and that's obviously going to be 0. And then we're going to have u is equal to the tangent of pi from the left over 2. And we already know that for tangent, it's increasing. So pi over 2 from the left, that's going to be equal to positive infinity. And then it's going to go to negative infinity immediately thereafter. So that means this is going to be the tangent of pi from the right over 2. So that's going to be equal to minus infinity. And then we're going to have u is equal to the tangent of 2 pi over 2. So that's going to be equal to the tangent of pi. And we know that's going to be equal to 0. So here we're going to have our first set of bounds. And then here we're going to have our second set of bounds. And we already know how our sines and or cosines, even though there's no cosines, and dx are going to change under the Weierstrass substitution. Okay? So let's combine all of this together. So we have our integral, for which I'm going to represent by star. Again, is the integral from 0 to pi of sine of x dx all over 1 plus sine x. And I'm going to split this into two integrals and add them up. So this is going to be equal to the integral from 0 to pi from the left, and then the integral from pi to 2 pi, right? So that's going to be our integration, and then we're going to turn this into sine of x all over 2 plus the sine of x dx, and then use our Weierstrass substitution and rewrite sine in terms of 2u all over 1 plus u squared. So therefore our integral will be equal to the integral from 0 to pi plus the integral from pi to 2 pi of, and keep in mind these integrals are in terms of u, not x, and this is going to be equal to 2u all over 1 plus u squared. So that's the top sine, and then we also need to do the same for the bottom, all over 2 plus 2u all over 1 plus u squared. So that's the interior. And then we need to rewrite our dx term. So what is dx? Well, dx is just going to be equal to 2 all over 1 plus u squared multiplied by du. Right? Now you have to do some algebra to clean this up, obviously, because that's just nasty to look at. Multiply top and bottom by 1 plus u squared, and then that'll clean things up quite a bit. So we have the integral from 0 to pi plus the pi and then pi to 2 pi for our integrals. And then that's going to be equal to 2u all over 1 plus u squared times the reciprocal of the bottom, which is going to be equal to 1 plus u squared all over 2 times 1 plus u squared plus 2u times 2 all over 1 plus u squared du. Lots of cancellations going on here. We have those particular things. And we also have, what do we have here? We have that 2. We have that factored 2 cancel out. We do still have this 2 on the outside, which we're going to bring to the front of both of our integrals. And then what are we going to have left? So we have a u chilling on the top. And we also have this bottom stuff going on here, right? So u squared plus 1. And then u squared plus 1 plus u on the bottom there. Okay, so let's just clean this up a bit. So our integral of interest will be 2 times the integral from 0 to pi plus the integral from pi to 2 pi of, let's see, what is this? So we have u divided by, let's write this as u squared plus 1, and then u squared plus u plus 1, and then we're just going to have that multiplied by du. So we have two things that are pretty decent. Keep in mind u squared plus 1 doesn't factor over the reals, and u squared plus u plus 1 also doesn't factor over the reals either. So if we use partial fraction decomposition on this particular integrand, you know, write it as a over u squared plus 1 plus b over u squared plus u plus 1. Find a and b in whatever methods you prefer. Then we're going to have what? Oh, also, wait a minute. Wasn't this bound supposed to be like something else? I think we changed our bounds already, didn't we? I think we changed them to like 0 to infinity, minus infinity to 0. Let's go back before we forget that. Where would that change? Oh, that would start changing right here. So let's just adjust that. Oh, my integral disappeared. My 0 to infinity, 0 infinity, minus infinity 0, and then this would also be 0, infinity, minus infinity, 0. Okay, cool. So everything's fine there, and now we just need a partial fraction decomposition that. You might want to pause the video and see if you can do that on your own. So 0, infinity, minus infinity, 0. But this will actually come out as actually something pretty nice. So that's integral of 1 plus u squared minus 1 over u squared plus u plus 1. And everybody should be able to do those individual integrals out on their own. In particular, the first one's extremely easy. That's just the arctangent. And then you should be able to complete the square on this object. Because what's that? Well, that's u squared plus u plus 1. So the magic number in front of u this time is 1. Divide that by 2 and square it. So that's going to be equal to u squared plus u plus 1/4 minus 1/4 plus 1. And what is 1 minus 1/4? Well, that's just going to be 3/4. And that little underlined term, that's just going to be equal to u plus 1/2 the quantity squared plus 3/4. And then you can write that in terms of a trigonometric substitution if you want, but nonetheless, you should be able to know that that's just the arctangent of a scaled linear function. So once we have all that done, then our magical little integral will just be equal to what? So we have the arctangent of u minus 2 divided by the square root of 3 times the arctangent of 2u plus 1 all over the square root of 3. Now, what about our boundaries? Because keep in mind we had two integrals, right? So we had the integral from 0 to infinity and then minus infinity to 0, which, keep in mind, is the same as the integral from minus infinity to 0 plus the integral from 0 to infinity. So if this integral doesn't have any issues at 0, then we can technically glue these integrals together. So if we plug in 0, notice that that doesn't have a discontinuity at 0 because that's almost like a bell curve. And the 1 over u squared plus u plus 1 also has a bell-shaped like curve. It's just shifted. And that's obviously clear from the completing the square perspective. So since u is not an issue, then the only boundaries that we really need to consider here are the integral from minus infinity to infinity, right? So that actually makes life a lot easier. So if we go to this integral, we just need to take this integral, send it to infinity, send it to minus infinity, and then have a good day with that. So what is that? So keep in mind the arctangent is just a tangent sort of sitting on its side with horizontal asymptotes at plus or minus pi over 2. So this is going to be equal to what? So arctangent of infinity, that's going to be pi over 2, minus the arctangent of minus infinity, that's going to be minus pi over 2. So that's going to be negative pi over 2, which is going to give us a total of pi. We have this minus 2 over the square root of 3. And what is that? 2u. So 2 times infinity is infinity, plus 1 is infinity, divided by a finite number is infinity as long as it's positive. So that's still going to be equal to the arctangent of infinity minus the arctangent of minus infinity. So that's still going to give us our typical pi over 2 minus negative pi over 2 as a result there. So once we have that, what are we going to be left with? And I believe I forgot our lonely little 2 out front. Oh, there they are. So this 2 needs to come down. Don't run away from us. So that's going to be equal to 2 times 2. And that's going to be equal to 2 times what? So pi over 2 plus pi over 2 is going to be equal to pi, minus 2 over the square root of 3. Pi over 2 plus pi over 2 is going to be equal to pi. And then you can do whatever you want to this expression. You can write it as like 2 pi times 1 minus 2 over the square root of 3, I guess. I think that would be a nice expression, right? So therefore what? So therefore we can write our original integral, which was the integral from the 0 to 2 pi, of the sine of x all over 1 plus the sine of x dx. And we have proven this is just going to be equal to 2 pi times 1 minus 2 divided by the square root of 3. And wasn't that fun? Right? And that was able to be generated from the Weierstrass substitution. Very, very beautiful and clever technique. So those are some of the things that you definitely can do with trigonometric substitutions. Yes, the algebra can be extremely complex, but the beauty and the number of integrals that you can solve with that complexity definitely become extremely, extremely large. So I hope you enjoyed this video, and I'll see you in the next one. Take care.